Okay, phase diagrams. This is sort of like a map of the state of a substance. Phase is another word for state, meaning, the physical state, solid, liquid, gas. And so in this map, we have pressure on the y-axis and temperature on the x-axis. And I'll just give you a quick look at this one. So here's pressure and temperature. And there are some lines here that represent phase changes or state changes. And then there are regions that represent regions of pressure and temperature where the solid is stable. So we've got regions where that particular state is stable. We have lines or curves that represent a set of temperatures and pressures where there's an equilibrium between the two states, where you have the solid and the liquid present, or the liquid and the gas. And those are named for their state transitions. And then we have the triple point. And the triple point is a unique combination of temperature and pressure where all three states are stable and in equilibrium with each other. That's pretty cool. So here's the phase diagram for water. And the diagrams are going to look a little different for each substance. Here we have the sublimation curve along this line, and that shows, at this temperature and pressure, at this temperature and pressure, you'll have both the gas and the solid in equilibrium with each other. Here's the triple point where you'll have all three of them. Above here, this is the vaporization curve between a liquid and a gas. This is the fusion curve. And the critical point, this is the critical temperature and critical pressure, and above that, you have a supercritical fluid. You do not have a liquid or a gas. And so that line ends, just ends. There's no division after that. So let's look at a cool video. So here's a video demonstrating the triple point. This is for tertiary butyl alcohol. So they're pulling a vacuum on this flask. Nothing happens. Oh, starts to boil. They're continuing to lower the pressure. Notice they're not heating that. It's boiling at room temperature. Stops boiling. You see over here, there's a solid in before. It's freezing. And it's boiling. So you've got freezing and boiling happening at the same time, same substance. The liquid, the gas, and the solid in equilibrium with each other. Freeze and boil at the same time. It's at that triple point, yeah.
This is all by vacuum?
Yeah, they're just lowering the pressure. And they kept lowering it, and they got below that triple point. Now it's all frozen. Okay, so we saw the triple point for tertiary butyl alcohol. This would be the triple point for water. And so what they were doing is they were starting at a particular temperature, which is room temperature, at a pressure, and then they decrease the pressure. That particular substance was boiling first. Water, if you did that, it would freeze first, and then it would begin to boil down here. So it would look different, but that's the general idea of the triple point. So you need to be able to navigate within a phase diagram. So the way we do that is, you've got a particular point. And so for here, 1 atmosphere, this line A, so at 1 atmosphere, taking the temperature of water from minus 25 degrees Celsius up past 100 degrees. As we go along at a constant pressure, we see that there's this transition from the solid to the liquid, and it's a liquid, it's a liquid, it's a liquid, and then it transitions to a gas. Or you can change the pressure. You can start here at atmospheric pressure, 25 degrees Celsius, room temperature, lower the pressure, lower the pressure, lower the pressure. At this point, the water will boil at room temperature. My high school chemistry instructor did that in class and made us all come up and touch the flask. First person was a little scared. Who wants to put their hand on boiling water, right? It was room temperature. And you keep going and it'll all be gas at room temperature. Here are a couple of other substances. Here's iodine and carbon dioxide. And their phase diagrams have different shapes. The most notable thing is the slope of the fusion curve line. So if you look at water, water's fusion curve has a negative slope. As you increase in temperature, the pressure gets lower. And what's cool about that is if you put pressure on ice, you can actually cause it to melt a little bit. So here you're at atmospheric pressure and a given temperature, and by increasing the pressure, you can cause the water to melt. That's how ice skates work, and things with runners, like sleds with runners. The pressure from your weight on those little tiny ice skating blades causes the top surface of the water to melt, the ice to melt, causing it to be much more slippery. And so you can glide around and do all kinds of cool stuff. Well, some people can. This is more typical, where this line has a positive slope. Another notable thing is for carbon dioxide, here's 1 atmosphere of pressure, normal pressure, and as you go across increasing temperature, there is no temperature at which the liquid exists. And that's why carbon dioxide always sublimes at atmospheric pressure. You can only get the liquid at very high pressures. Any questions? The triple points, are in different places. Here, this is at minus 56. Here, this one is at 114. For tertiary butyl alcohol, it's near room temperature, and that's why you can do that, cool them off.